Welcome to the deep dive. Now, if you're currently working through the AMT Powerplant course, maybe getting your hands dirty, this session is absolutely for you.
Yeah, we're aiming to give you that critical edge today.
Our goal here is to cut through some of the complexity, really zero in on the essentials of engine maintenance, both recip and turbine.
Right, moving from the nitty-gritty of overhaul all the way to understanding those crucial operational limits you'll be dealing with out on the line.
We're digging into the source materials, the manuals, trying to bridge that gap between just knowing a definition and truly understanding how it applies in practice.
Exactly. It's about the practical knowledge, the stuff that keeps your certification valid, and more importantly, keeps those engines turning safely.
Okay, so let's start where maintenance planning really begins. It often centers around this key term, time before overhaul, or TBO. We need to be crystal clear on what this means.
Absolutely. TBO, well, it's the manufacturer's specified lifespan for an engine, usually given in operating hours. Once an engine hits that number, it must come out of service for a mandatory overhaul.
And that number isn't just pulled out of thin air.
Not at all. It's based on tons of testing, stress analysis, understanding fatigue, material limits. It's all very calculated.
So let's play devil's advocate. What happens if someone pushes past TBO? What's the actual mechanical risk we're trying to avoid?
You're fundamentally risking component failure, parts exceeding their safe operating limits. Think about the really stressed stuff, crankshaft journals, connecting rods, gears. They accumulate fatigue over time. Going beyond TBO means you're operating in a zone where the chance of a structural failure due to that built-up stress just gets unacceptably high. Airworthiness demands predictability. TBO sets that boundary.
Makes sense. Could you give us a quick example calculation just to make it concrete?
Sure, pretty straightforward.
Yeah.
Let's say the manufacturer dictates a 2,000-hour TBO for a particular engine model. You check the logbook and it shows 500 hours flown since it was new or since its last major overhaul.
Okay.
Simple math. 2,000 minus 500 leaves you with 1,500 hours remaining on that TBO clock.
And a proper overhaul resets that clock.
Correct. A correctly performed major overhaul brings the engine back to a zero-time state, legally considered as airworthy as a brand new one. But, and this is a big but, only if that overhaul process, the inspection, the parts replacement, the reassembly, is done absolutely by the book, flawlessly.
Okay, let's shift gears to reciprocating engines. Our sources lay out the procedures pretty clearly. When an engine needs work, we often hear about two main levels, major overhaul and top overhaul. What's the real difference on the shop floor?
Well, the main distinction boils down to how much you take apart, and that directly impacts the scope of the inspection. A major overhaul is the whole 9 yards, complete engine recondition.
A full teardown.
Exactly. The FAA definition specifically requires the crankcase to be separated or disassembled. You take everything apart. Every single piece gets cleaned, inspected, measured. It's either repaired, replaced, or confirmed as serviceable based on strict limits.
And it's not just the core engine, right? Accessories, too.
Absolutely. All the bolt-on stuff, magnetos, pumps, carburetor, starter, they all have to come off, be overhauled according to their manufacturer's specs, and then tested. It's comprehensive.
Okay, so that's major. What about the top overhaul? Sounds less involved.
It is. The name kind of gives it away. You're overhauling the parts on top of the crankcase.
Cylinders, pistons.
Right. Cylinders, pistons, rings, the whole valve train mechanism. But crucially, you do not split the crankcase. The bottom end, the rotating assembly, stays untouched.
So why would you do just a top overhaul?
Usually it's a response to a specific problem, like maybe premature valve wear causing low compression, or maybe bad piston rings leading to high oil consumption. It's classified as a repair procedure, not a full overhaul.
Given how interconnected everything is, I'd imagine there's some debate about just doing the top end.
Oh, absolutely. That's the modern thinking. While it's a valid repair, many experts today argue against it if you could avoid it. Their point is, if the wear up top is bad enough to need new cylinders or pistons, the root cause might actually be deeper. Maybe it's related to crankcase alignment or bearing issues down below.
So fixing the symptom, not the cause.
Potentially, yes. Plus, the labor involved in a top overhaul. It can get surprisingly close to the labor for a full major overhaul anyway. So the recommendation often is just bite the bullet and go for the major overhaul. Ensure the whole engine's integrity.
Makes sense. Let's focus on that major overhaul then. It's often presented as a 10-step process. Which of those steps demand the most intense focus and skill?
Without a doubt, the inspection phases. Visual inspection, structural inspection using NDT, and dimensional inspection. Those are the heart of it.
Why so critical?
Look, taking an engine apart. Anyone with decent mechanical aptitude can learn that. putting it back together correctly, also achievable with care. But determining if a used part, maybe slightly worn, is still safe to fly for another TBO cycle. That takes judgment, precision, and strict adherence to the manufacturer's data.
The final call rests with the technician.
Entirely, based on their inspection and measurement against the published limits. It's a huge responsibility.
Okay, let's walk through the start. Step 1 and 2. Receiving inspection and disassembly. What has to happen before a single bolt is turned? Paperwork first.
Absolutely. Documentation is paramount. First thing is grabbing the engine's logbooks. Think of it as the engine's life story. You review its entire history. Then you meticulously inventory all the accessories. Record their model numbers, serial numbers, everything.
And compliance checks, ADs and SBs.
Critical step. You have to cross-reference the logbooks against all applicable airworthiness directives. ADs, those are mandatory FAA fixes and relevant service bulletins from the manufacturer. SBs might be recommendations, but often they address important safety or reliability improvements. You must verify compliance status for all ADs.
Only then you get hands-on.
Only after all that paperwork is squared away and compliance is verified. Then you can finally mount the engine on an overhaul stand and give it an initial external cleaning.
All right, engine's on the stand. We're moving into disassembly. What are the key disciplines here? Keeping things organized.
Organization is everything, non-negotiable. Parts need to be laid out systematically. People often use partition trays or shadow boards. Why? Because many internal parts are matched sets. Like a specific piston belongs with a specific connecting rod in a specific cylinder location.
Right, they've worn in together.
Exactly. Even if they pass inspection, they generally need to go back exactly where they came from. You're preserving that engine's internal history as you take it apart.
And the oil drain procedure, I remember reading something specific about that.
Yes, very important diagnostic step. When you drain the old oil, you must strain it, usually through a fine mesh screen, sometimes even cheesecloth. Then you carefully inspect whatever gets caught in the screen or cloth. Look for metal particles.
What does that tell you?
It's immediate feedback on potential failure modes. Are the flakes bronze-colored? Maybe a bushing is failing? Steel particles? Could be a gear or bearing issue. Aluminum, piston or case problem. The type and amount of metal is crucial info.
Good point. And safety devices. Wire, cotter pins.
Hard rule. Always dispose of and replace all safety devices. No exceptions. Safety wire, cotter pins, tab washers, even certain types of self-locking nuts. They are designed for one-time use. Their locking properties are compromised after removal.
Reusing safety wire is just asking for trouble.
Absolutely. Vibration is relentless. You need fresh locking devices torqued correctly. And one more thing on disassembly. Always use the right tools. The manufacturer's manual specifies special tools for a reason. Using makeshift tools or the wrong size wrench is the fastest way to damage expensive parts and get them rejected.
Okay, the engine's disassembled, parts are laid out clean. Well, maybe not quite clean yet. The technician's real detective work starts now with visual inspection. But you mentioned a specific order. Visual before heavy cleaning. Why look at the dirty parts first?
Because the dirt tells a story. Those residual deposits, traces of metal, patterns of oil burning, localized carbon buildup.
Yeah.
They are evidence. They might be the only clues pointing to how a part failed or where a hidden weakness lies. If you immediately blast everything clean in a degreaser.
You wash away the evidence.
Precisely. That initial visual inspection is diagnostic. You're trying to understand the failure before you start the cleaning and repair process.
Got it. Now let's get into the language. Every AMT needs to know this defect terminology cold. First up, Brinelling. What is it and where do you typically find it?
Okay, Brinelling. Think smooth, rounded dents. You find them primarily on bearing races, the tracks that ball or roller bearings run on.
What causes those dents?
Usually one of two things. Either the bearing was subjected to a really high static load for a long time, like an engine just sitting in a crate, maybe vibrating slightly during shipping. Or, more commonly, it's damage from improper installation or removal. Someone using a hammer to tap a bearing into place instead of pressing it correctly.
The percussive force.
Yeah, the balls or rulers literally get pressed into the softer race material, leaving those characteristic indentations.
Okay, next term, galling. Sounds pretty severe.
It is severe. Galling is a nasty form of surface damage. It's described as extreme chafing or fretting, but the key is there's actual transfer of metal from one surface to another.
Wow. Metal physically moving.
Yes. It happens when you have slight movement, often microscopic, between two parts that are under very high pressure or load. Classic examples are the fit between a piston pin and its bushing, or maybe between the back of a bearing insert and the connecting rod bore it sits in.
And the implication of finding galling.
It generally means the part is rejected. Galling indicates the metal structure itself has been weakened or distorted at that point, and the critical precision fit is completely ruined.
All right. How about corrosion and pitting? We see that everywhere.
Right. Corrosion is just a chemical breakdown of metal, zinc, rust on steel, or oxidation on aluminum. Environmental attack, or attack from combustion byproducts like acids. Pitting is the result you see. Tiny, irregular little hollows or craters on the surface.
Is all pitting bad?
Depends where it is. A little light pitting on a non-stressed surface might be allowable, maybe polish out. But pitting in highly stressed areas, that's a major red flag.
Like where specifically?
The classic example is the fillet radius of a crankshaft journal, the curved transition where the journal meets the crank cheek. Pitting there is a huge stress riser, a potential starting point for a fatigue crack. Same goes for the inside surface of a piston pin. If you find pitting in those critical zones and it can't be removed with very light polishing, the part is scrap.
Okay. We also need to distinguish between two kinds of abrasive wear, abrasion versus scoring.
Good distinction. Abrasion is generally caused by fine particles, dirt, gosto, maybe fine carbon getting between moving parts. It results in a sort of general surface roughness, maybe lots of very fine scratches.
And scoring.
Scoring is much more dramatic. Think deep, distinct scratches or grooves, usually caused by larger, harder particles getting trapped, or sometimes by a temporary loss of lubrication, causing metal-to-metal contact under load. It's generally a more severe condition than simple abrasion.
Let's apply this to specific parts. The cylinder head. What are the critical inspection points there?
Cylinder heads are all about managing heat, so you look at the cooling fins first. Externally, a small crack right on the edge of a fin might be okay if you can smoothly blend it out by filing, and it doesn't go too deep.
But cracks at the base are different.
Totally different. A crack at the base of a cooling fin, where it joins the main head casting. That's cause for rejection. Same if a crack penetrates through to the inside. Internally, you look for cracks radiating from the high-stress areas, usually around the valve seat bosses or the spark plug holes, often caused by overheating or improper torque during assembly.
Got it. Now, the crankshaft. Arguably the backbone of the engine. What's the absolute first check during its overhaul inspection?
First thing, before almost anything else, is a run-out check. You have to check if the shaft is bent or warped.
How's that done?
You set the crankshaft up on precision V-blocks, supporting it on the main bearing journals. Then you use a dial indicator placed on the other journals and slowly rotate the shaft. The indicator measures any deviation from perfect concentricity.
And there are strict limits.
Absolutely. The manufacturer's manual specifies the maximum allowable runout. If it exceeds that limit, the crankshaft is rejected. And there's a critical safety rule here.
Which is?
Never, ever attempt to straighten a bent crankshaft.
Why not? Seems like you could just bend it back.
You'd think so, but no. High-performance crankshafts, especially the journals, have an extremely hard surface treatment. Often it's nitriding, which creates a thin but very hard wear-resistant case. If you try to bend that shaft even slightly, you risk creating microcracks in that brittle nitrided layer or even rupturing it.
Compromising the wear surface.
Exactly. You might get it dimensionally straight, but you've destroyed the integrity of the bearing surface. It will fail very quickly once back in service. So bent shaft equals rejected shaft, period.
Okay, visual check's done. Now we actually get to clean the parts. But even this sounds like it has pitfalls. Let's talk degreasing. What are the hazards with cleaning chemicals?
Well, standard commercial solvents are used for basic degreasing. The big caution flag comes with some water-mixed cleaning solutions, especially if they contain caustic compounds, strong soaps, or alkaline chemicals.
Why are those risky?
They can be extremely corrosive, particularly to the lighter alloys like aluminum and, even more so, magnesium. Worse, these chemicals can sometimes get trapped in the slightly porous surface of castings if they aren't completely removed.
Perhaps enough later.
Big problems. Long-term hidden corrosion, or when the engine heats up in operation, the trapped chemicals can leach out into the oil and cause serious oil foaming. Foaming oil doesn't lubricate well.
So the key is thorough rinsing if you use those types of cleaners.
Absolutely critical. If you use any water-based or caustic solution, you have to rinse relentlessly, often with hot, clean water to make sure every trace of the chemical is flushed out. And then immediately after cleaning and drying, you must coat the parts with a light layer of preservative lubricating oil.
Why immediately?
To prevent flash rusting on steel parts or just general corrosion starting on any bare metal exposed to shop humidity. You need to protect them until they get reassembled.
Okay, that handles grease and grime.
Yeah.
What about the really baked-on stuff, the hard carbon deposits, especially in piston ring grooves or combustion chambers?
Yeah, that needs a more aggressive approach. Usually involves soaking the parts in a specialized, often heated decarbonizing solution for a set time. After soaking, the softened carbon can be removed, typically by brushing, maybe some careful scraping with non-metallic tools, or sometimes by grit blasting.
Ah, scraping. Are there places you absolutely should not scrape?
Oh, definitely. Huge rule. Never use wire brushes or metal scrapers on any bearing surface or precision contact surface. You'll scratch or score the finish. Remove critical surface hardening or alter dimensions. Absolutely forbidden. Use soft brushes, maybe plastic or wood scrapers, if needed, very carefully.
Makes sense. You mentioned grit blasting. I've seen different materials use sand, glass beads, even walnut shells. How do you choose, and what's the big safety precaution?
The choice of media depends on the base metal and how much cleaning power you need. Crushed walnut shells or baked wheat kernels are softer, good for general cleaning without removing metal. Glass beads give a finer, peened finish. Sand is more aggressive.
And the safety rule.
Masking and plugging. This is non-negotiable. Before any grit blasting, every single machine surface, every bearing bore, every threaded hole, every oil passage, everything that isn't being intentionally blasted must be meticulously masked off with special tape or plugged with appropriate plugs.
Why so strict?
You cannot risk getting abrasive grit into an oil passage where it will cause havoc later, or onto a precision-bearing surface where it will destroy the finish. Contamination is the enemy. Sometimes, maybe valve seats might be very lightly blasted to break a glaze before grinding, but even that requires care. Generally, protect everything critical.
All right. Parts are sparkling clean. Now we verify their structural integrity with non-destructive testing, NDT. These find the flaws our eyes miss. Let's start with the one for steel parts, magnetic particle inspection.
Right. Mag particle, or MPI, is specifically for ferromagnetic materials, basically iron and steel. Your crankshaft, connecting rods, steel cylinder barrels, gears. How it works is you induce a magnetic field in the part. Then you apply fine iron particles, either dry powder or suspended in a liquid.
And the particles reveal the cracks.
Exactly. If there's a crack or flaw on or near the surface, it interrupts the magnetic field lines. It creates a tiny magnetic leakage field. The iron particles are attracted to this leakage field and pile up directly over the crack, making an invisible flaw visible. It's very effective, but useless on aluminum, magnesium, titanium, etc.
So for all those non-magnetic parts, engine cases, aluminum pistons, magnesium accessory housings, we need something else, dye penetrant inspection.
Correct. Dye pen, or LPI, liquid penetrant inspection, works on virtually any non-porous material. The key requirement is that the defect must be open to the surface. It won't find purely internal flaws.
And it's a multi-step process.
Yes, a very specific sequence. You absolutely have to follow it correctly. Step 1, clean the part meticulously. Surface must be spotless. Step 2, apply the penetrant. This is a brightly colored, usually red, or fluorescent liquid that has very low surface tension, designed to seep into tiny cracks. Step 3, dwell time. You let the part sit for a specified time to allow the penetrant to fully penetrate any flaws. Step 4, remove excess penetrant. This is critical. You carefully wipe or wash off the penetrant from the surface without washing it out of the flaws themselves. Step 5, dry the part thoroughly. Step 6, apply the developer. This is usually a fine white powder, often sprayed on. It acts like a blotter, drawing the penetrant trapped in the cracks back out to the surface, creating a visible indication of a red line on a white background or a glowing line under UV light if using fluorescent penetrant. Then you inspect and interpret.
Technology gives us more advanced tools, too. How does eddy current inspection fit in?
Eddy current is really versatile and often faster. It uses electromagnetism. A probe induces small electrical currents, eddy currents, in the part surface. Flaws like cracks, corrosion pitting under the surface, or even variations in material conductivity or heat treatment will disrupt the flow of these eddy currents. The instrument detects that change.
What's a major advantage?
A big one is that you often don't need to remove paint or surface coatings, like anodizing, to perform the inspection. That can save a huge amount of prep time compared to, say, dye penetrant. It's great for finding surface and near-surface defects quickly.
And lastly, ultrasonic inspection, using sound waves.
That's right, high-frequency sound waves, way above human hearing. A transducer sends pulses of sound into the material. These sound waves travel through the part and reflect off boundaries like the back surface or internal flaws like cracks or voids. The instrument analyzes the timing and strength of these reflections.
Different methods for different goals?
Yes. Pulse echo is common, where one transducer sends and receives. Through transmission uses two transducers, one on each side, measuring the signal loss. And resonance testing is specifically good for measuring thickness very accurately, especially when you can only access one side of the part, like checking cylinder wall thickness.
Okay, structural integrity confirmed. Now we get down to the micrometer level. Dimensional inspection. This is where we measure everything against the manufacturer's specs, right? The table of limits.
Exactly. This is pass-fail time based purely on numbers. Use precision tools, outside micrometers, inside mics, telescoping gauges, bore gauges to measure every critical dimension. You compare your measurement to the limits published in the manufacturer's overhaul manual. There are usually limits for a new part and then wear limits or serviceable limits.
And if a part is worn beyond that serviceable limit,
It has to be either reconditioned to an approved undersize or oversized dimension, if allowed for that part, like grinding a crankshaft journal undersize, or it must be rejected and replaced. There's no wiggle room. The numbers dictate the decision.
let's focus on the cylinder barrel. We measure it in several places, typically top and bottom, and often at 90-degree orientations. What wear patterns are we looking for?
Three main things caused by operational wear and tear. First is taper.
Meaning the diameter isn't the same top to bottom?
Correct. Taper is the difference in diameter between the top part of the barrel, near the combustion chamber, and the bottom near the skirt. You'll almost always find the top diameter is larger, it wears more.
Why does the top wear more? Heat and pressure.
Exactly. The top few inches see the absolute highest temperatures, the highest pressures during combustion, and also the greatest side loading from the piston and connecting rod as the piston changes direction. It's just the harshest environment in the cylinder.
Okay, so taper is one. What's second?
Out of roundness. We check if the cylinder is still perfectly circular, especially up top where the wear is greatest. We also check for out of round down at the skirt, the cooler bottom end. Damage there is less likely from operation, more often caused by careless handling, bumping, or dropping the cylinder during maintenance.
And the third wear indicator, something you can sometimes feel.
Yes, the step or ridge. This is a physical ridge that forms right at the very top limit of where the top piston ring travels. Over thousands of cycles, the rings wear away the barrel below this point, but not above it.
And why is that ridge a problem?
It's a huge problem if it gets too big. When you install new piston rings, that cop ring will slam into this sharp ridge on every upstroke. It can break the ring, damage the piston, or cause the piston to seize.
So it has to be removed.
Absolutely. If it exceeds the manufacturer's specified limit, you either have to machine the entire cylinder barrel oversize, which removes the ridge as part of the process, or if the ridge is very slight, within certain tolerances, you might be allowed to carefully blend it out using fine hand stones to remove the sharp edge.
Interesting. Now, there's also an intentional distortion built into some cylinders. Cylinder choke? What's that about?
Ugh, choke boring. It's clever engineering. Some manufacturers intentionally make the very top of the cylinder barrel, near the mounting flange, a tiny bit smaller in diameter than the rest of the barrel below it,
It's smaller at the top. Why?
to compensate for thermal expansion. The cylinder head area runs much, much hotter than the lower barrel during operation. Metal expands when heated. By making the top slightly smaller when cold, they ensure that when the engine reaches its normal operating temperature, that choked area expands just enough to become perfectly straight and cylindrical, matching the rest of the bore. It maintains the ideal piston-to-cylinder clearance when hot.
Very clever. Okay, moving down to the valves and valve seats. Refacing the seats, grinding versus cutting. What determines the method?
Primarily the seat material. Most modern engines use hardened steel valve seats. Steel is best refaced using precision grinding stones. You get a very accurate angle and a smooth finish. Older engines, or some specialized applications, might have used softer bronze valve seats. Bronze tends to clog up grinding stones quickly, so for bronze, the traditional method is to use specialized valve seat cutters or reamers.
Got it. Now, a really critical concept, the interference fit between the valve face and the seat. We actually grind the valve face angle slightly different from the seat angle, like maybe a 44.5-degree valve face on a 45-degree seat. Why do that?
Yes, that small difference, usually between 0.5 and 1.5 degrees, creates what's called an interference angle or interference fit. It's done for a very important reason. It ensures that when the valve first closes against the seat, the initial contact isn't across the entire width of the valve face. Instead, it makes contact only on a very narrow line, typically right at the maximum diameter of the valve face against the seat.
A line contact, not a surface contact initially. Why is that better?
Two main reasons. First, that concentrated line contact creates a very high seating pressure right away, promoting a quick, positive, gas-tight seal. Second, and perhaps more importantly, think about engine break-in. During the first few hours of running, the valve is literally pounded into the seat by combustion pressure. That narrow line contact allows the valve to seat itself in more effectively and progressively, forming a wider contact band over time. It dramatically reduces the chance of hot combustion gases leaking past during those critical early hours, which could easily burn the valve or seat.
So how do you verify you have the contact right before you put the cylinder head back together?
You use a visual check, most commonly with Prussian blue dye. You apply a very thin, even coat of the blue paste to the valve seat. Then you carefully place the valve into the guide, press it firmly onto the seat with light pressure, and give it maybe a quarter turn or just lift it straight out.
And look at the mark left on the valve face.
Exactly. The blue dye transfers to the valve face where contact was made. You're looking for a clear, continuous blue line or band. Ideally, this contact band should be positioned roughly in the middle of the valve face, not too close to the edge margin and not too close to the stem. And its width should typically be about 1/3 to 2/3 the total width of the valve face itself.
What if the contact band is too high or too low?
Then you need to adjust the seat. There are special grinding stones or cutters used to narrow the seat angle or change its position slightly up or down to bring that contact patch into the desired location on the valve face.
And the absolute final check for sealing.
After everything looks right, you do a valve leak test. You install the valve, springs, retainers. Then you apply some finger pressure on the valve's stem head to hold it closed, simulating spring pressure. You lay the cylinder head on its side and pour a solvent, like clean kerosene or mineral spirits, into the intake or exhaust port cavity, filling it up above the valve head.
And watch for leaks.
Yep. You watch the area around the valve head inside the combustion chamber very closely for several minutes. If you see any seepage or wetness appearing around the valve margin, it means the valve is not sealing perfectly. You've got to go back and figure out why, maybe relap it lightly or re-inspect the seat and face angles.
Makes sense. Briefly on pistons and pins. Besides obvious scoring or damage, what else are we looking for?
On the piston head, you check it for flatness, usually with a straight edge. If you see any dishing or depression in the center of the crown,
That's a sign of
detonation. Severe detonation creates incredibly high, sharp pressure spikes that can literally hammer the piston crown concave. Finding that means the engine has likely suffered significant abuse. You check the ring grooves very carefully for wear, especially widening or damage to the groove lands. Often use a new ring and a feeler gauge to check side clearance.
But pistons often get replaced anyway.
Quite often in a major overhaul, yes. Given the intensive labor needed to meticulously clean carbon out of ring grooves and inspect them perfectly, it's frequently more cost-effective just to replace the piston and ring assembly. For the piston pins, you look for scoring, overheating discoloration, and galling. If they are the case-hardened type, which is common, they absolutely must get magnetic particle inspected. Pay special attention to the inside surface of hollow pins, as cracks can initiate there.
All right, the engine is rebuilt, hopefully perfectly. Now we transition to putting it back into service safely. Before the very first start attempt, what should the manifold pressure gauge be reading in the cockpit?
Good pre-start check. With the engine off, the MAP gauge should simply be reading the local atmospheric pressure, also called barometric pressure.
So around 30 inches of mercury at sea level.
Roughly, yes. Maybe 29.92 HDs on a standard day, but it varies with weather and altitude. The key is that it should reflect the ambient air pressure. If it's reading significantly lower, maybe you've left an intake plug in. If it's reading way off, the gauge itself might be faulty. It's a good basic sanity check of the induction system reading.
After an overhaul, the engine's oil system is essentially dry. Pre-oiling is mandatory. What's the goal here, beyond just getting oil in?
The main goal is to purge trapped air from the oil galleries and passages and ensure that all the bearings and moving parts have a film of oil before they experience any rotational load.
How is it done?
Two common methods. One is to remove the spark plugs, so there's no compression load, and crank the engine over with the starter motor until you see oil pressure register on the cockpit gauge. The other method, often preferred, is to use an external pressure pot or pump. You connect it to the oil system, usually at a pressure port, and force clean engine oil through the galleries until you see pressure indicated and maybe oil flow at the rocker arms. This ensures thorough lubrication without rotating the dry engine.
Okay, now for a classic safety procedure, especially critical for radial engines. Preventing hydraulic lock. What causes this?
Hydraulic lock is a real engine killer, particularly in radials or inverted engines where cylinders point downwards. During shutdown or even just sitting, lubricating oil from the crankcase or sometimes unburned fuel can drain down under gravity and collect in the combustion chambers of the lower cylinders.
And liquids don't compress.
Exactly. Liquid is effectively incompressible. So if you try to start the engine, when that piston comes up on its compression stroke, it runs into this solid slug of oil or fuel. The engine stops dead instantly.
What breaks?
The weakest link, which is almost always the connecting rod. The force is immense and instantaneous. You'll typically bend or even snap the connecting rod. Requires another teardown, major repairs, catastrophic.
So how do you prevent it? What's the mandatory check procedure?
Before attempting to start any radial engine, or any engine type prone to it that has been sitting, you must check for hydraulic lock. The procedure is remove at least one spark plug from each of the lower cylinders, the ones pointing downwards or horizontally at the bottom. Then, you slowly pull the propeller through by hand for several complete revolutions, at least 2 or 3 full turns. And critically, you must turn it only in the normal direction of rotation.
Why never turn it backwards?
Good question. If you turn it backwards, opposite the normal direction of rotation, any liquid pooled in the intake pipe could potentially get sucked backwards past an open intake valve of another cylinder, setting up a hydraulic lock there instead. Turning it forward ensures that any liquid trapped in the combustion chamber is safely pushed out through the open spark plug hole. Any liquid in the intake pipe gets pushed toward the cylinder and eventually out the exhaust valve when it opens. Always turn forward.
Got it. Let's quickly touch on the instrument markings. The color codes on engine gauges universal language, right?
Absolutely. Every pilot and technician must know these instantly. Red line or red radial arc. This marks the absolute limit, maximum or minimum. Never operate in the red. Exceeding a red line means potential damage or failure. Think max CHT, max RPM, minimal pressure, yellow arc. This is the caution range. Operation is permitted, but usually for limited times or under specific conditions and requires close monitoring. A classic example on a carburetor temp gauge is the yellow arc from about minus 10 degrees C to plus 15 degrees C, indicating the range where carb icing is most likely.
And green.
Green arc. This is the normal, safe, continuous operating range. Keep the needles in the green for normal flight phases, and you're operating within the engine's design parameters for longevity.
Okay, operational hazards. 2 big combustion problems. Detonation and pre-ignition. They sound similar but are distinct. Can you break down the difference?
Yes, very important distinction. Detonation happens after the normal spark plug firing. The spark initiates a flame front, moving across the combustion chamber. Detonation is when the remaining unburned fuel-air mixture ahead of that advancing flame front spontaneously explodes due to excessive heat and pressure, rather than burning smoothly.
Like a secondary explosion.
Exactly. It creates an incredibly rapid, uncontrolled pressure spike, like hitting the piston top with a hammer and intense localized heat. This is what causes that hammering noise and can lead to severe engine damage, like cracking piston rings or even burning a hole right through the piston crown.
How do we prevent detonation?
It's about controlling the conditions. First, use the correct specified grade of fuel. Higher octane fuel resists detonation better. Second, use richer fuel mixtures at high power settings. The extra fuel provides evaporative cooling inside the cylinder. And third, strictly respect the engine's operating limits. Don't exceed maximum manifold pressure or RPM for the conditions.
Okay, so that's detonation. What about pre-ignition?
Pre-ignition is simpler, conceptually. It's when the fuel-air mixture ignites before the spark plug is scheduled to fire.
What causes it to light off early?
Usually a hot spot, somewhere in the combustion chamber. This could be glowing carbon deposits, a sharp edge on a valve, an overheated spark plug electrode tip, or even damage caused by previous detonation. Anything hot enough to ignite the mixture before the spark.
And the result?
Very rough running, and usually a very rapid runaway increase in cylinder head temperature, CHT, because combustion is happening way too early, fighting the piston's upward travel. Pre-ignition is extremely destructive and can melt pistons very quickly. If suspected, power must be reduced immediately.
Checking cylinder health often involves a differential pressure tester, or diff check. How does that work and what does it tell us?
The differential compression tester is a great diagnostic tool. It measures how well the cylinder holds pressure which tells you about the sealing of the piston rings and the valves. The setup involves bringing the piston to top dead center, TDC, on its compression stroke, so both valves are closed. You then screw an adapter into the spark plug hole and apply regulated air pressure, usually 80 psi, into the cylinder. The tester has two gauges and a calibrated orifice between them. One gauge shows the input pressure, 80 psi. The other shows the pressure actually being held inside the cylinder. The difference indicates leakage.
So a reading like 75/80 is good.
Yeah, 75-80 psi would be considered pretty good leakage, only 5 psi lost. The manufacturer specifies the minimum acceptable reading, maybe 60-80 or 65-80. Below that, you have excessive leakage. But the number is only half the story. The crucial part is figuring out where the air is leaking from.
How do you do that? By listening.
Exactly. You listen carefully. If you hear air hissing out of the exhaust pipe, that's a leaking exhaust valve. If you hear it coming from the air intake or carburetor, that's a leaking intake valve. If you hear air hissing out the engine crankcase breather tube or the oil filler cap, that indicates air blowing past the piston rings.
Clever. What if you get a low reading, say, from a suspected valve leak? Is there a quick field fix to try? I've heard of staking the valve.
Yes, that's a valid technique, but use it carefully. If you suspect a small piece of carbon might be trapped on the valve seat, causing the leak, staking might dislodge it. Use a fiber drift or brass hammer and give the rocker arm directly above the valve stem a sharp, firm tap. The idea is this slight movement and vibration might shake the carbon particle loose.
And then retest?
Crucially, yes. After staking, you must rotate the engine crankshaft through a couple of revolutions to allow the valve to rotate and potentially reseat itself properly. Then you reperform the compression check on that cylinder. If the reading comes up, you likely cleared the debris. If not, the valve likely has a more serious sealing issue.
Okay, we've spent a lot of time on recip engines, the overhaul philosophy, the inspections. Let's pivot now to turbine engines. The maintenance approach here feels a bit different, often more focused on condition monitoring, but inspections are still key. Let's start at the front. The compressor or cold section, what's the biggest enemy here?
Without a doubt. FOD, foreign object damage. It's the constant nightmare for turbine operators and maintainers.
Meaning things getting sucked in.
Precisely. Compressor blades are spinning incredibly fast, made of strong but relatively delicate materials. Even a small object, a forgotten tool, a rivet, a bolt, sometimes even ramp debris like gravel or ice getting ingested can cause massive damage. One damaged blade can shed pieces that then take out subsequent stages. It's a cascading failure. So tool control, keeping work areas clean, and thorough inlet inspections before every single run are absolutely paramount.
What if a blade just gets a small nick or dent? Can that be repaired or is it always replaced?
It depends entirely on the manufacturer's limits, which are very specific. Minor nicks or dents, especially on the outer half of the blade or on the edges, might be repairable. The repair usually involves carefully blending out the damaged filing or stoning to remove the sharp edge and create a smooth, rounded contour. The blend must be smooth, polished, and always oriented parallel to the length of the blade to minimize stress concentration.
Are the limits the same everywhere on the blade?
No, definitely not. The limits for repairable damage are usually much, much tighter on the inner half of the blade, closer to the root or hub. That part of the blade sees the highest centrifugal stress loads, and the absolute hard rule, no cracks are ever permissible in a compressor blade. Any crack, however small, means the blade must be replaced.
Okay, moving back to the hotter parts. The combustion and turbine sections, collectively the hot section. What are the key inspection points here? This is where the real heat stress happens.
Right. Externally, you look at the engine case for any signs of buckling, bulging, or discoloration hotspots that might indicate an internal problem like a burn-through in a combustion liner. Internally, usually using bore scopes for on-wing checks or during shop visits when the modules are open, you're inspecting the combustion liners, the turbine nozzle guide vanes, which are stationary, and the turbine rotor blades themselves.
Looking for what specifically?
Cracks, certainly. Warping or distortion from heat, evidence of burning or erosion, and again, any signs of FOD that might have made it through the compressor. Over-temperature damage is a major focus.
How does that over-temperature damage manifest itself on, say, a turbine blade? Is there a classic sign?
Yes, the telltale sign of prolonged or severe over-temperature operation is stress rupture cracks.
Stress rupture.
Yeah.
What do they look like?
They are typically very fine, almost like hairline cracks. You find them on or across the leading or trailing edges of the turbine blades or vanes. The key identifier is their orientation. They run at right angles, perpendicular to the edge itself. They occur because the metal, under high stress and excessive heat, has actually started to creep or stretch beyond its elastic limit over time. Finding these is definitive proof the engine has been run too hot, and those blades are compromised.
Replacing turbine blades isn't just about swapping parts, though. There's a critical balancing act involving moment weight limitations. Can you explain that?
Ah, yes, moment weight. This is absolutely critical for the smooth operation and longevity of the turbine rotor. Because these disks spin at such incredibly high speeds, even tiny imbalances can cause destructive vibrations. So each individual turbine blade is precisely weighed, and its center of gravity is determined. From this, a moment value is calculated, essentially weight times distance from the center of rotation.
And they're installed based on this value.
Exactly. Blades are usually sorted and coded based on their moment weight. When building up a turbine disk, they are installed in carefully matched pairs or sets, often following a specific sequence around the disk, for example, installing them in diminishing moment weight order. The goal is to distribute the mass as evenly as possible.
So what if just one blade gets damaged by FOD and needs replacing? You can't just swap that single blade.
Generally, no. Because of the critical balance, if you have to replace one blade, you almost always have to replace the blade that is located diametrically opposite to it on the disk, 180 degrees across. You replace them as a pair using two new blades that have a matching moment weight code close to the ones being removed to maintain that essential rotor balance.
Makes sense. What other critical measurements are taken in the turbine section during inspection? Clearances?
Yes, checking clearances is vital, particularly the turbine blade tip. Clearance the gap between the rotating blade tips and the stationary shroud or casing around them. Also, clearances between other rotating and stationary parts, like the turbine wheel stages relative to the exhaust cone or nozzle diaphragms. These are measured using specialized feeler gauges or sometimes optical methods.
Why are these clearances so important?
If the clearance is too tight, the blades could rub against the shroud as they expand thermally during operation, causing wear or even failure. If the clearance is too large, excessive amounts of hot gas will leak past the blade tips instead of doing useful work, which significantly reduces engine efficiency, power output, and increases fuel consumption. It's a critical tolerance.
Okay, maintenance covered. Let's talk about operating these turbines safely. The starting sequence seems pretty specific. What's the correct order of events?
Very specific and critical for preventing damage. The standard sequence is 1. Engage the starter to get the engine rotating, establishing airflow through the compressor and turbine. 2. Turn the ignition on-in. You need the spark source ready. 3. Introduce fuel by moving the throttle or fuel control lever to the idle or start position. This order, air, spark, fuel, ensures you have sufficient airflow to support combustion and carry heat away before the fuel lights off. Getting it wrong invites trouble.
What kind of trouble? What are the immediate abort start conditions pilots watch for?
Two main ones, the hot start and the hung start. A hot start is when the exhaust gas temperature, EGT, climbs way too rapidly and exceeds the specified starting limit. Usually caused by too much fuel too soon or not enough airflow, maybe a weak starter or strong tailwind. A hung start is when the engine lights off, okay, EGT might be normal, but it fails to accelerate to the proper self-sustaining idle RPM. It just hangs at some lower speed, often due to insufficient starter power or some engine issue.
And if either happens?
Immediate abort. You cut the fuel flow instantly by moving the throttle fuel lever back to OOF. Critically, for a hot start, you often keep the starter engaged for a period afterwards.
Why keep motoring it?
To blow large volumes of cool air through the engine, purging the unburned fuel, and, more importantly, rapidly cooling the turbine section that just experienced the temperature spike. This helps prevent thermal damage.
After a flight, especially after high-power settings, there's a required shutdown procedure involving a cool-down period at idle, maybe 5 minutes. Why is this necessary?
It's all about managing thermal stresses during cooling. The turbine wheels themselves are massive, dense metal components. They heat up significantly during operation and hold that heat for a long time. They have high thermal inertia. The outer engine casings, however, are thinner and exposed to cooling airflow, so they cool down much faster once power is reduced.
Ah, so differential cooling rates.
Exactly. If you shut the engine down abruptly from high power, the outer case starts to cool and shrink fairly quickly, while the big turbine rotors inside are still expanded from the heat. This can cause the shrinking case to bind or seize on the still hot turbine wheels, leading to rubs, distortion, or even stress cracks. Letting the engine idle for a few minutes allows the internal temperatures to stabilize and normalize across the engine before shutdown, preventing this stress.
There's also a specific sequence for the fuel pumps during shutdown. turn off the boost pump after the main fuel lever?
Yes, that's generally the procedure. The electric fuel boost pumps in the tanks provide positive pressure to the inlet of the high-pressure, engine-driven fuel pump and fuel control unit. These engine-driven pumps are intricate, precision devices that rely on fuel flowing through them for lubrication and cooling. By moving the main throttle or fuel shutoff lever to off at force, you stop fuel flow to the engine, but keeping the boost pump on for a few moments longer ensures the engine-driven pump remains filled with lubricating fuel until it completely stops rotating.
Prevents it running dry.
Exactly. Running those high-pressure pumps dry, even for a short time, can cause rapid wear and potential seizure.
Let's talk instruments. In the cockpit, EGT is prominent. But what do maintainers consider the single most critical variable for monitoring turbine engine health?
It really still comes back to exhaust gas temperature, EGT. While we monitor lots of parameters, EGT gives the most direct indication of the thermal stress being experienced by the hottest parts of the engine, the turbine section. It's our best practical approximation of the turbine inlet temperature, TIT, which is the actual temperature of the gas hitting the first stage turbine blades. TIT is the true limiting temperature, but it's extremely difficult to measure directly in that environment.
So EGT is our window into TIT.
Pretty much. We know the relationship between TIT and EGT for a given engine design. By keeping EGT within its prescribed limits, we are indirectly controlling TIT and ensuring the turbine blades aren't exceeding their temperature limits, which prevents creep, stress rupture, and ensures maximum component life.
How do pilots typically set power on a big turbofan engine, like on an airliner?
On most turbofans, thrust is set using engine pressure ratio, EPR. EPR is simply the ratio of the total pressure measured at the engine exhaust, station PT7, divided by the total pressure measured at the engine inlet, station PT2. It gives a direct measure of the overall pressure increase across the engine, which correlates very closely with the thrust being produced.
But that doesn't work for turboprops, right? Most of their thrust comes from the propeller.
Correct. On a turboprop, the exhaust gas pressure contributes only a small fraction of the total propulsive force. So EPR isn't a useful indicator of the power being delivered to the propeller. Instead, turboprops rely on a torque meter. This instrument measures the actual twisting force, or torque, being delivered by the engine's gearbox to the propeller shaft. It's usually displayed in units like foot-pounds or shaft horsepower, or sometimes as a percentage of maximum rated torque. That's the primary instrument for setting power on a turboprop.
Since EGT is so critical, its accuracy must be spot on. How is the EGT system calibrated, and what's the big danger if it's inaccurate?
Accuracy is absolutely vital. The EGT system uses thermocouples junctions of dissimilar metals that generate a tiny voltage proportional to the temperature difference between the hot junction in the exhaust stream and a reference junction. Even being off by just 10 or 20 degrees Celsius consistently can drastically shorten the life of expensive hot section parts. Calibration is usually done using specialized test sets, like a bar field or jet cool analyzer. These testers can simulate thermocouple outputs, check the resistance of the entire circuit, thermocouples, wiring, connectors, indicator, and verify the accuracy of the cockpit gauge itself.
What's the most dangerous failure mode in that EGT circuit?
By far the most dangerous is a high-resistance fault developing somewhere in the circuit. This could be a slightly loose or corroded cannon plug connection, a frayed wire, or even an issue within the indicator itself. High resistance impedes the flow of that tiny electrical voltage signal from the thermocouples to the gauge.
Then what does that do to the reading?
It causes the EGT indicator in the cockpit to read falsely low.
Ah, that is dangerous. The pilot thinks they have temperature margin they don't actually have.
Precisely. The pilot, trusting the gauge, might push the engine harder, thinking they're still within limits, when in reality the actual turbine temperature, TIT, could be exceeding the red line. This leads to insidious over-temperature damage creep, erosion, stress rupture, accumulating without any warning, potentially setting the stage for a catastrophic turbine failure down the road. That's why checking EGT system resistance and accuracy is such a critical maintenance task.
Wow. Okay. This has been a really comprehensive journey. We've navigated through the meticulous steps of reciprocating engine overhaul, highlighting critical inspection terms like galling versus Brunelling, and the reasons behind procedures like interference fits.
Yeah, and we covered crucial safety procedures like the hydraulic lock check, understanding detonation versus pre-ignition, and the importance of differential compression tests.
Then we shifted to turbines, focusing on FOD prevention, hot section inspection signs like stress rupture cracks, the complexities of moment weight for blade replacement, and vital operational limits tied to EGT.
The common thread through all of it, whether recic or turbine, is precision. Following the manufacturer's data to the letter, using the right tools and techniques, and really understanding why these limits and procedures exist.
That understanding is fundamental for anyone pursuing their AMT Powerplant certification. Knowing the difference between a major and top overhaul isn't just academic. Knowing why you never straighten a crankshaft or why tip clearance matters, that's the practical knowledge that ensures safety.
Absolutely. It's about internalizing these principles so they become second nature on the hangar floor.
So we've established that traditional time before overhaul, TBO, is primarily driven by accumulated operating hours, a limit based on historical data and material fatigue curves. But think about the technologies we've discussed today.
Like advanced NDT, finding tiny flaws, real-time monitoring.
Exactly. Consider non-destructive testing that can detect microscopic defects long before they become critical. And think about modern F8E systems. Full authority digital engine controls constantly monitoring dozens of parameters in real time. Vibration signatures, oil debris sensors, estimated TIT calculations.
Where are you going with this?
Well, here's the provocative thought. With all this data, all this insight into the actual condition of an engine moment by moment, could we eventually move beyond fixed, hour-based TBO?
You mean towards a purely condition-based overhaul system?
Potentially. Could future regulations allow an engine to continue flying as long as its real-time sensor data and detailed NDT inspections show it remains within safe operating parameters regardless of the hours flown? Making overhaul truly dependent on condition, not just the clock. That's a fundamental shift you might see and deal with in your aviation careers.